right there. So equilibrium, right, to solve for the external support forces. We've got an infinite number of equations available to us, and what we are going to use are 3. So the first thing we're going to do is spin a moment over at A. So if you want to kind of look below here, I'll highlight point A. That'll give us an equation that'll allow us to solve for F3. Next, we're then going to spin a moment over at point C. It's going to give us the ability to solve for F2. And then we can sum forces in the X direction to go ahead and solve for F1. So that would be a good scheme. And we come up with an infinite number of schemes because we actually have an infinite number of equations of equilibrium. Here, without using a sum of the forces, we'll end up solving for all 4 of them. I'm going to highlight the very last one here. We're going to define a point off the beam. This point E right here, it'll show up a little bit later. That point E will end up being somewhere right around there. And all we need is a point that is not on the line of action of F1. So again, as we've already solved for F2 and F3 above, then we would end up with one equation, one unknown. And then we will perform an independent statics check, which is taking the solved free body diagram, and we are going to perform another equation of equilibrium. And that equation of equilibrium, if our beam is if it's in equilibrium, we'll end up with 0 equals 0. So let's go ahead and execute scheme 1 here. So I'm going to back off some of that. And so let's go ahead and do that. Let's spin a moment over there at A. So again, anything that has a perpendicular distance is going to contribute to the moment about point A. I have used the sign convention of counterclockwise is positive. So about point A, I'm going to track all the loads that cause a moment. So that 500-pound force would cause a rotation about point A in the clockwise direction. So the contribution using the sign convention is going to be negative. Likewise, F3 and 800 are also going to have contributions. So you notice the lever arm for the 500-pound force is 6. Lever arm for the F3 is going to be 12. And it's 22 for the 800-pound load all the way out there. And so we end up solving for F3. We get a positive number. And that positive number relates back to the free body diagram. And so a positive number would mean that we have put the arrowhead in the correct direction. So the answer is the invariant representation of F3 would be 1717 pounds up. And so next we'll end up spinning a moment over at point C. And I'll give you a moment to do that. If you want to pause the video. So in the end, we end up with, again, about point C. Right? We end up with an equation that's going to have the 800, the 500, and F2 in it. And you see that there with different lever arms than what we had above. And in the end, mathematically, we end up with an answer that says F2 is equal to negative 417 pounds, which would mean that F2, as seen in the free body diagram, is actually going down. So we're going to knock off the last one, F1. We'll just sum forces in the X direction, and we end up with a answer of 0 right there. And so I'm going to lay out scheme 2 here for you and allow you to pause the video and take a shot at summing moments at C, summing moments at D, and then again summing forces in the X direction. There would be our answer, summing moments at point C as our first equation, ending up with F2 is equal to minus 417, or 417 pounds down. Summing moments at D, we end up with the exact same answer that we had for F3 in scheme 1. So it doesn't matter what order you do them. You have a bunch of different possibilities. And as a demonstration, what we will do is solve for F1 instead of using some of the forces in the X direction here. We'll go back to the solved free body diagram where we are currently. We've solved for those two reactions, so those two red arrows have been turned black. Going to define a point E, and that point E is going to be 2 feet above the beam. So let me just dimension that right there. That distance is 2 feet. It's going to be 5 feet off the right end of the beam as well. So again, there's point E. So I can find F1 if I spin a moment about point E. So I will give you just a minute to go do that on your own. So coming back, spinning a moment at point E. Again, we'll have 4 forces in it and the unknown force F1, so a total of 5. And again, we see the forces that we've already turned black in the other equations. And when we solve this, we end up with F1 equals -2. So we have a little bit of a contradiction here. We end up finding that F1 is equal to -2 pounds. And in another equation, we ended up finding out that F2 was equal to 0. And so the question is, which one is correct? Well, to do that, what we need to do is do an error analysis. So we need to compare the difference that we've got, this 2. We need to figure out if it's significant. And so what we need to do is compare it to other terms in that equation that it came from. So if we just compare it to this term up here, we're going to compare 2 to 5,500. And if we notice, if we do the percent difference calculation, we end up with much less than 1%. Again, in engineering, anything less than 3% is really just fine. So this is insignificant. So whether or not we say that F1 is equal to -2 or it's equal to 0, right, either answer would be acceptable. Here clearly 0 is the more correct answer because of some of the forces.